Welcome back, everyone. So our next lecturer is Professor David Berenstein from Santa Barbara. So David will go to the second part of the lecture, Introduction to the AdS CFT Correspondence. David, please.
Okay, thank you. Okay, so this is part two. So just reminding you what the statement of the AdS CFT correspondence is. The statement is that quantum gravity in some spacetime that is like AdS can be equivalent to a quantum field theory in fewer dimensions, which is what the CFT side is. And yesterday, we spent some time understanding a little bit of what CFT is and a little bit of where AdS came from. And today, we need to understand a little bit more the physics of AdS and how to relate it to physics of CFT in more detail. The original example, the simplest one, which is the one that I've been talking about, says that n equal 4 Yang-Mills, that was the theory in the D-branes. And here I'm cheating. I'm putting in a cylinder on S3 times R. So we saw via the operator state correspondence yesterday that the cylinder was a good place to start talking about states and operators. So we do it here. And this turns out to be equivalent to type 2B string theory on AdS 5 cross S5. And it's going to be the same AdS 5 cross S5 that we had before. It's just that instead of being something that's written in Poincare slices, which is what we did, it's going to be global AdS 5 cross S5, which is what we're going to talk about today. And then in the original Maldacena paper, where this duality was established, this was not S3, this was R3, 1, and this was Poincare slicing of AdS 5 cross S5. And then there's some global issues that get complicated when you do that, and some other calculations become simpler. Okay. So when we talk about near horizon and having something like a horizon, that's not true about AdS 5 cross S5 in the global geometry any longer. That's true about a particular patch of the geometry where you can make a horizon. So there's going to be some slight change in geometry from yesterday to today in what we mean by AdS 5. I mean, globally, they're different objects. Locally, they're the same. Okay. The table that sets up a correspondence is that in AdS, we have some isometries. And that's what corresponded in the conformal field theory to the global symmetries. There was a radius of AdS in string units. That's some parameter. It's the size of AdS in the fundamental units. That was matched to the 't Hooft coupling constant in the conformal field theory. In the AdS geometry, we had n D-branes, and D-branes carry a charge. So when you think about the S5 has a flux that measures how many D-branes were in there. That flux is n. And that quantization of the flux, Dirac quantization, is what corresponds to the fact that the gauge group is UN. If the flux were not quantized, this number would be continuous. And then the gauge group would be U with some irrational number in it, or something like that. So the point is that this is quantized already in the classical physics by describing the gauge group. Here, the quantization, the solution of gravity, comes from requiring that the flux be quantized in the sense of Dirac. So there's a little bit of quantum mechanics to say that this is an integer already hiding in the AdS side. Okay. And then the statement is that it is an equivalent of Hilbert spaces. So states here need to be mapped to states here. And therefore, the one state that we think we know, which is the vacuum of AdS, is going to be mapped to the vacuum of the conformal field theory. And the vacuum of the conformal field theory in the operator state correspondence is the trivial operator called the identity, the one that doesn't do anything. Okay. And then that's the one state that we think we know how to match. And then the rest is to build on top of that, to build on top of the vacuum. So the idea is that gravity works well in the sense of classical physics or semi-classical physics when this number is big, meaning that the string scale is much, much smaller than the size of AdS, so that you can actually do classical GR and stuff like that for a while before having to deal with string phenomena. And so long as that scale of strings can be made much smaller than gravity, you can do classical gravity. The way we usually do that is we just solve gravity equations classically. And then that works well when this number is big, and that's the strong coupling limit of the field theory in the sense of 't Hooft. Okay, So as I talked yesterday, when you talk about quantum field theory states on the cylinder, we use the operator state correspondence to map local operators, which is something that's easy to visualize. You have a table of fields, you just build local operators easily. And then that gives you a map to states on the cylinder. And the idea is that we use the operators many times as a proxy for the states, but I'm like Hamiltonian physics, so I really like to talk about states. Okay, so you've seen a lot of situations in this workshop where people say physics is, and they write a path integral, and they use this Lagrangian formulation. For me, physics is the Schrodinger equation, which is, IDT of psi is equal to the Hamiltonian times psi. We know they're equivalent, but thinking Hamiltonian sometimes gives you a very different way of analyzing the problems than Lagrangian physics. The descendants are you act with the operator P on the sets of O's, acting with P on the operators is trivial. They're generated by derivatives. So I can write the list of descendants trivially in the operator language by just taking derivatives of the operators. And then you say, okay, I got my list of descendants. If I know the operators, I can write the derivatives. So all I need is the operators. And that was basically the idea. And then the operators that are important are these primary states, the ones that have some special property with respect to the conformal field. Okay, so now we go to gravity. So we're going to work in AdS5. So what do we need to do to classify states? So we need to quantize fields on AdS. This is what the idea of semi-classical gravity is. You have some gravity theory with some fields. It doesn't matter what the fields are. You pull them out of a hat, but they're there. They're given to you. And then they say, do quantum field theory on AdS for these fields. And then basically, how do you quantize free fields on AdS? You need to solve the wave equations of AdS. And then, once you solve the wave equations, we know how to do particles and antiparticles and the usual quantum field theory gadgets. Why do we do this? Because it's what we know how to do. Yes?
Yes, this is it. I haven't figured this technology out. Okay. I mean, you can do the tree diagrams, of course, but
Yes.
you're going to loop diagrams are still going to be divergent.
Yes.
So what do you do?
Not there yet.
You don't go there. Just this is tree level classical.
You do tree level classical, and then you start there.
Okay.
The point is, how do we do quantum gravity? We do perturbative quantum gravity by first analyzing the perturbative modes, and then burying the infinities that show up by a prescription. And if you're a smart string theorist, you know what some of these counterterms will be, and then you put those numbers in there when you need them.
But there's a sort of standard cutoff that one uses in AdS to do this?
String scale.
Oh, okay.
For example. Okay. The idea is, the first thing you do is you do classical physics, and then you just solve the wave equations and find your single particle states and go from there. The question about the cutoff is, once you quantize, what do you do? But before you quantize, you first need to do classical physics. So you solve the equations of motion. Okay. So I'm going to solve the equation of motion by doing a clever analytic continuation so I don't have to work. There's two ways of solving equations of motion. You just write your wave operator, separate variables, and do the calculation. Or you say, I have a lot of symmetry, I can solve it by symmetry. Okay, so I'm going to solve it by symmetry, and I'm going to cheat by doing analytic continuations on something you all know. So AdS space is actually a type of analytic continuation of a sphere. So if I tell you, do the spherical harmonics of a sphere, this is what you've done in your electrodynamics classes in Jackson. So you have your sphere, and then you know how to do that. So I'm going to tell you that the process of solving the wave equation over here is the same as the process of solving spherical harmonics on the sphere. So what do I do to make AdS space? There's a representation of AdS space where you take this object over here, which has all plus signs, and then you get the correct signature to get SO4, 2 by changing two of these plus signs to two minus signs. And then you might be concerned that in a geometry like this, I might have two time-like directions. But that's not necessarily the case. If I would put a +1 here, that would be the case that there will be 2 times. If I put a -1 over here, the constraint will eliminate 1 time like direction and give me only 1 time. So the induced metric on this hyperboloid of something that has signature d, 2, the induced metric on it has signature d, 1. So it has the correct space-time structure to be something where you can define a wave equation, and it's the Lorentzian AdS. Okay. Again, this is just a statement about how to write the homogeneous space that was the sphere and analytically continue it to something that has the correct isometry in the correct metric. Okay. So the next thing I need to do is tell you how to build the coordinate system of AdS by analytically continuing your random coordinate systems on the sphere. So how do I make a coordinate system on the sphere? I split the d+1 dimensions, or the d+2 dimensions I have here. I have d+2 dimensions. I split them into a group of k+1 coordinates and d+1 minus k. And if you add these two up, you see that you get k+1 plus d+1 minus k. The k+1 and the minus k cancels, and you get d+2 directions. And then I just write my spherical or my coordinates of the vector space in polar coordinates for these k+1 directions and in polar coordinates for these d+1 minus k directions. So in each one of them, there's a radial direction, R1, R2. There's some k-sphere over here, some d minus k-sphere over here. So I've written my flat space coordinates in terms of polar radial coordinates in some decomposition of the space. And then I have 2 radii. Now they're both positive. And then I say I'm going to go to polar coordinates of R1 and R2. So there's a common radius, which is R1 squared plus R2 squared. That's R. And then there's an extra angle, which is the one between the two. And then once you put in that R1 is R cosine theta and R2 is R sine theta, you can just fill in the pieces over here. The dr1 squared plus dr2 squared becomes a standard polar coordinates in 2 dimensions. And then you have these extra angles and this decomposition over here. Okay. So I just constructed a whole bunch of different coordinate systems for you on the sphere. And now I project to the sphere, which is r squared equal to constant. So I get rid of the dr squared and all the factors of r squared. And I produce for you volume elements for the sphere in various coordinate systems. So this is what you do in the coordinates that I gave you, y1 through yd+2. And now I claim that you go in an analytic continuation from one to the other one. And I need to do a split, which the best split is to split this 2 away from this d. So you do a 2 plus d split. And when you do this 2 plus d split, what that means is you do k equal 1, because it was k+1 and d+1 minus k. So you get k equal to 1, and you split the line element. And then you do the analytic continuation where theta goes to I theta. And then the cosine of theta becomes a cosine hyperbolic squared of theta. And then the sine of theta becomes an hyperbolic square of theta. And because you did an analytic continuation, cosine and sines have different values of I. So when you square them, one gets a plus sign and the other one gets a minus sign. So when you look at this stuff over here, you get a cosine hyperbolic squared. You get a sine hyperbolic squared. There's a minus sign over here, which comes from, how did I do that analytic continuation from theta to I theta? And then I relabel my theta coordinate with this minus sign here and this stuff over here. And I call it a radius coordinate, and I call it rho. So if you look at this expression over here, the line element of anti-zero space has a radial direction, cosine hyperbolic rho squared times dt squared. This is the time direction, and this is the warp factor. So cosine hyperbolic has a minimum at rho equal to 0. That's what we call the bottom of AdS, right? That's the place of maximum redshift. And then when rho goes to infinity, you get infinite blue shift, meaning that the clocks start running faster and faster as you go to infinity. And then there's a sphere over here, and the radius of the sphere is hyperbolic sine squared of rho. Okay. This is what are called global coordinates in AdS space, and the signature is d space-like and 1 time-like. Okay, so what I've told you is how to go from the standard, let's say, algebraic coordinates to the trigonometric coordinates on the sphere that one would use.
I'm just tempted to say, if you're a Euclidean approach person,
Yes.
you make a plus sign in front of that T.
Yes.
The Hamiltonian is still a Hamiltonian.
Right.
And so you can do it that way as well. And that
Right.
would be the natural way, which you could do put it on a computer.
As I said, I like Hamiltonian physics. So
No, but it's
if,
still,
if you did that, you
it's
would
still-
still have a negative number here, and you would change one
I'm
of
sorry,
these to a plus one.
it's Euclidean time, but it's still Hamiltonian physics.
Yes. No discussion there. But I like real time. There's a.
You can have minus or plus, it doesn't matter. We're not going to.
Okay. I heard that this was a quote that Witten made at some point. I'm not sure that this is, it sounds correct, but I don't know that is true, is that you should like Lorentzian physics, because here you have real time, and only in real time stuff actually happens. So, okay. This is a really important sign, and I want to keep it, okay? So what's the idea? The idea is that the y.
David, one question.
Yes.
Maybe you can draw the, you mentioned about the bottom of the AdS.
Yes.
Maybe you can make a drawing of this watt factor.
Okay. So cosine hyperbolic of rho. The rho coordinates is defined from rho equal to 0 to infinity. Cosine hyperbolic starts at 1, and then it grows exponentially. So this is what rho looks like in the rho coordinate. This is what the watt factor looks like. And then the minimal value of the dt squared is the value of y equal to 0. And again, this is a special locus in this coordinate system, which is the origin in the rho coordinate. It's only special in that sense. Okay, so I picked an origin. Okay. So the new variable rho that I invented here now is non-compact. It goes from 0 to infinity. It started as an angle, but now becomes a hyperbolic angle. But hyperbolic angles can be non-compact. And then this variable t that still looks like it's periodic. If you actually look at the proper geometry of AdS, this hyperboloid that I showed has a non-trivial pi1, and you need to unwind that pi1. And that means that the t coordinate over here, even though it shows up in the exponentials, this coordinate t is not periodic. The function yd plus 1 plus I have yd plus 2 is periodic, but the t goes from minus infinity to infinity. So once you go to the rho t coordinate system, in the rho t coordinate system, this t is not identified modulo to pi. This t really goes from minus infinity to infinity. So when I write things, I have to be very careful with that statement. Okay? This is an important statement. Okay, so in the change of coordinates, t appears in a periodic function in the y coordinates. So the y coordinates don't really cover AdS, they cover a slice of AdS, of global AdS. And then the idea is you make t, you analytically continue in t and make it go from minus infinity to infinity, and each value of t corresponds to different slices. And if you roll that all together, then you get this picture of the hyperboloid, and if you unwind it, then you go to the covering space of the hyperboloid. That's exactly part of the problem. You don't want them to be periodic, or you want them to, you want them to have a fixed frequency, but you don't want the frequency to be an integer. So that's how you. Yes. Yes. Okay. So the new variable in rho and t is non-compact, and you need to be careful. And then some people make mistakes exactly because they forget about this. And then when you do physics in the hyperboloid, you have closed time-like curves. That's not what we really want. The hyperboloid is a convenient set of coordinates for part of the problem, but they don't cover the full AdS. But it's a nice way to understand how to go from representation theory of the sphere to representation theory in AdS. Okay, so we have coordinates, and now that we have coordinates, you can solve the wave equation. Okay. These are the spherical harmonics. So the I here runs from 1 to d minus 1. Sorry. 1 to d. It goes from y1 all the way to yd. This is where the yi goes. And y0 and y minus 1 are treated slightly different because of the cosine hyperbolic of rho. So the idea is that the yi's, the ones that are not y0 and y minus 1, become hyperbolic sine of rho times some spherical harmonic on the sphere. And these are the usual story that the x, y, z are spherical harmonics with angular momentum 1. So it's that kind of statement. D plus 1, D plus 2, I make them complex in the original sphere. And then when I go to the analytic continuation, the cosine of theta becomes a cosine hyperbolic of rho, and the exponential of it stays exponential to height t. And then this becomes the y0 plus y minus 1. So this is sphere, and then below is the analytic continuation to the Lorentzian case. Okay. We have coordinates, now we can solve the wave equation. So how do we do this? And now this is where I'm going to cheat, and I'm going to tell you, how do you find all the spherical harmonics of the sphere? You actually don't have to work directly on the sphere. You can work on the vector space R to the D. So you take a scalar function on a sphere. You can be written usually on spherical harmonics. And these are the representations of the symmetry group of the rotation group of the sphere, on the functions. These are in one-to-one correspondence with harmonic polynomials in one extra dimension. So you fill the sphere, you fill the extra dimension, you write your spherical you write your coordinate system as dr squared plus r squared omega squared, the omega squared. So you write the polar decomposition of your coordinates, and then you ask to have a harmonic function on the full space. And because r and the angles separate variables, you can separate the variables of the radial direction and the spherical harmonics. And then if you're solving the Laplace equation, the function of r will be correlated with the function that you get on the spherical harmonics. This is what you do when you do your favorite multipole expansion in electrodynamics. You have spherical harmonics, and then you have polynomials in inverse powers of r and positive powers of r. Okay. So if you actually pick the ones that are polynomials, the function at angular momentum L has a power exactly r to the L. So the point is that this is a polynomial of degree L in the original variables, y1 through yd. Okay. Again, this is a statement about how to generate the spherical harmonics. What I want you to take home is the idea that spherical harmonics are the same thing as polynomials of the x coordinates of fixed degree. Okay, and then you divide out the radius, but it's really important that you have these polynomials. Okay. So your general polynomial of degree d will be some tensor times the variables. This is one way to write it. Okay, so it's a general polynomial, so it's a sum of things of fixed degree with all possible entries. Because the y's are variables that we use commuting, the a needs to be symmetric. And then when you apply that, this needs to have vanishing Laplacian. When you act with the Laplacian on this object, you find that you're taking the trace of two of these indices over here, the a. So that has to vanish. So the tensor that shows up here, the set of possible polynomials, is constrained in that it is not a generic polynomial of degree d, but it's a symmetric polynomial, which is traceless, meaning that the tensor coefficients that show up here, the trace of those coefficients vanishes exactly. Okay, so the statement about representation theory is that this is the set of all the polynomials. When you do representation theory, it's also convenient to pick the highest weight state and then build the representation from that object. And the highest weight state is usually the one of maximal angular momentum. So you pick maximal angular momentum, and then you pick some set of two coordinates, y1 plus iy2, and you take them to the nth power, and that guarantees that you have maximal angular momentum on the 1,2 plane. So this polynomial, because of the facts of I, when you put the Laplacian over here, because it is holomorphic, it automatically vanishes. This is one of the properties of holomorphic functions, that they're harmonic.
What is a trace on a multi-index thing? What do you mean by trace?
The A is a symmetric traceless tensor with the indices. So you can contract the indices.
Oh, sorry. Any contraction is zero.
Yes, because it is totally symmetric. So any contraction can be made as a contraction of the first two indices by shuffling the indices.
So you just, okay, so you only need is identify any two indices, sum and get zero.
Yes, because any two indices are the same, they can be put in the first two indices. Yes. Okay. That's what the traceless part is, that when you contract, you get zero. But this is the nomenclature that is used, for example, in representation theory. Okay. So the highest weight state is of the form y1 plus I weight. Okay. Sorry, yes, it should be L indices. This should be IL and this YL. Yes, absolutely. The highest weight state of spherical harmonics is, again, a polynomial of degree L. This is the simplest one that I can write. And then it's maximal angular momentum, and that's what makes it the highest weight state. Okay. So what I do is I take the D and the D plus 1 and the D plus 2 coordinate, and I make them into a complex coordinate to the F power. And I analytically continue this to y0 plus I y minus 1. And then this thing that was here L, I call it minus delta. This is just a change of nomenclature. So this is what I call the variable z to the minus delta. Okay. I didn't do anything. I just took the highest weight state and I analytically continued the highest weight state to SOD, 2. Yeah, no, that was one that I just, it's YD plus 1 and IYD plus 2. Right? It's the one that goes to Y0 and Y minus 1. So again, the idea is that this is Z to minus delta. And then you need to have some convergence at infinity. So the idea is that since the variables are now non-compact, the wave functions that I want them to be sufficiently normalized. So I need this stuff to die off at infinity somehow. Okay. You can ask, why don't I do negative powers in the sphere? Is because Z can take the value 0. And therefore, if I put Z to the minus some number over here, I get a big singularity on my function. So my function is not regular. In AdS space, because of the minus 1 side, the norm of Z is always bigger than 1. So just the fact that I called it Z minus delta doesn't mean that there's a singularity at Z equal to 0, because Z equal to 0 is not really part of the domain of the function. So what happens here is that Z to minus delta is a perfectly well-defined regular function that happens to kind of vanish at infinity. And it has a weight Z to minus delta. And then the reason why delta will be positive is because you want your wave function not to blow up so badly that things go out of hand. Okay. So what we usually call the K generator ends up being mapped to Y derivative with respect to Z bar plus Z derivative with respect to YI. The delta generator is Z bar dZ bar minus Z dZ. And then when you take this delta acting as a differential operator on this object, you get the eigenvalue being equal to delta. So the idea is that we can basically understand that from the point of view of representation theory of the symmetry algebra, this object behaves nicely like one of these primary operators in that it has a fixed weight, and then I have K, and you can check quickly that K acting on this object is 0 because the Z doesn't depend on the YIs, and the Z doesn't depend on Z bar, so both of these terms kill it, and therefore K acting on the object is 0. And this is the differential equation analog of the primary field that Ki acting on the phi is equal to 0. Okay, so all I've done so far is showed you that after a clever trick, I managed to build a highest, well, it's the lowest weight state in the sense of the algebras, but it's what's called a primary operator in the sense of state representations of the conformal group. Okay. So what happens with my differential operators? I can generate a representation from the primary by acting with the p's, and the p's keep the degree of the polynomial or of the function fixed, because all the generators of the algebra are of degree 0, meaning that they don't change the degree of the polynomial. So you look at this, y has degree 1, derivative has degree -1, the degree of all of these gadgets is 0. So when you start with a primary, you can basically generate the rest of the representation by acting with P. That part of representation theory is the same as before because it's the same in the algebra, so it's the same representation content. And what you generate is that you were generating some set of harmonic functions or some type of polynomials of fixed degree that are irreducible representations of SO2, D. They are kind of harmonic in the sense that the functions were harmonic polynomials in the y variables in the original sphere. And they're polynomials of degree minus delta, which are polynomial in y1, yd, z bar, and they have poles in z inverse. But I told you that z equal to 0 never shows up in the space I have. And the idea is that once you have all these objects generated by symmetry, it turns out that these are solutions of wave equations in AdS with what people call a mass. The mass is the Casimir that you get from the group element, from the quadratic Casimir. This is what you get for the quadratic Casimir in d dimensions. This is the L times L plus 1 that usually you get in first Riker harmonics. And then because L was changed to delta, and there were some changes in signs, the mass becomes delta times delta minus d. So the analytic continuation gives you very quickly this delta times delta minus d condition. And the mass squared is what people call this combination. So if you know delta, you know m squared. If you know m squared, you don't know delta, not immediately. Delta is one of the two roots of that polynomial, and you have to pick one. And once you pick the correct root, then you can build a representation. But just by saying that you have a mass, that doesn't automatically give you delta immediately. In most cases, only one of the roots is positive and the other one is negative. And therefore, you just keep a positive root because that's the one that converges sufficiently well. And then m is equivalent to delta. But there's some special cases where m is small, where delta and d minus delta, which is the other stuff that will show up, can both show up in the calculation. So this is part of the dictionary that Witten wrote, and when Gutser-Kleban and Bolyakov wrote their papers, this was basically part of the dictionary that how do you relate dimension to mass squared? It was something like this. Okay, I've done it backwards. I first constructed a representation, the dimension, and then built m squared, rather than starting from n squared and trying to do it the other way. Okay, AdS is an infinite volume manifold. Rho is non-compact. Rho can go to infinity. So we must understand what happens at infinity. So what is infinity in this case is what happens when rho is equal to infinity. So all members of the same representation, they're polynomials of degree minus d or minus delta. So when you take rho to infinity, any one of those polynomials, no matter what they are, because they have a fixed degree, they all decay the same way as exponential of minus delta. Why? Because the yi's, including the y0 and all the y's, every single one of them, including z and z bar, grow exponentially in rho. In one case, it's a cosine hyperbolic. In the other one, it's a sine hyperbolic. But you know, I'm not going to quibble about that. They're both exponentials times some function that depends on theta and t. So every single one of these harmonic functions that you have here, when you try to go to infinity, decays in the absolute same identical way, right? This is a really important observation. This is actually something very, very, very important because we can define what people call a boundary field value, which is you take the limit when rho goes to infinity of your field, and then you chop off the bad behavior and you basically subtract that. So you say there's a way to take a limit, which is the asymptotic value of the field, where I understand how the field decays asymptotically, and I take that away, and I look at the coefficient of that. And that's what I would define the field at infinity. And why do we want to do that? The idea, in some sense, is because of holography. You know that you want to go to the boundary of the region. The boundary is rho equal infinity, and you want to be able to do some holographic map to that thing. So it turns out that the right thing to do will be to take a limit like this on everything. Here, right now, all I'm telling you is that because I have some nice asymptotic behavior, I can define a function on the boundary that depends only on time and these angles, which is this limit. If you see time and the angles, you would say, wait a minute, he seems to be talking about a cylinder. How did that happen? And notice also that the generator of dilatations, delta, when you go and do it in the t coordinates and everything, you go all the way back to here. This generator over here is really the generator that takes derivatives with respect to t this time that was showing up in z and z bar. Right? So this one is the one that is derivative with respect to t. So delta is what I would usually call the Hamiltonian. Right? It's the derivative with respect to time. So things that have a fixed derivative with respect to time have a fixed frequency. That's what's going to become my Hamiltonian. Okay, so very good. Okay, so when you act with the P has a fixed weight with respect to time because the P operator has either derivatives with respect to z bar, with respect to z, or multiplications by z bar. Each one of those has weight 1 with respect to Fourier modes, so each one of them adds a unit of frequency to time in a particular way, okay? So when you act with P, you change the frequency of your wave by a fixed amount, and the step is controlled by the Lie algebra, okay? So when you write different descendants, they give different frequencies in the time coordinate, okay? And then for large radius, the asymptotics, you still keep the fact that there was some non-trivial frequency dependence of f of delta. So it still depends on time. And that frequency shows up in the asymptotics over here. So these functions over here will be oscillating in time. And then the frequency of oscillation will be differing by steps of 1 in angular frequency. And if you have steps of 1 in angular frequency, you know that you can recover all the Fourier modes by taking a time of size to pi. This is a statement about recovery. It means that you don't need t from -infinity to infinity to recover the Fourier modes. The Fourier modes are discretely spaced. So if you have something that covers the difference in frequencies, then you can recover the amplitudes. So this is a statement about Fourier analysis. And this boundary field value that I just constructed is what we will need to understand the AdS dictionary. So I just told you something. I told you, you take this limit, it exists. And then I'm going to tell you that this is the most important part of the calculation, is that the existence of this limit is the thing that will let you map to the conformal field theory. Questions? I saw it. No? No questions? Okay. Obviously, this requires more elaboration. What is the boundary of AdS? Okay, this is the really important question. I just told you how to write the coordinate system in my favorite coordinate system, and I want to understand what happens when rho goes to infinity. So if you look at the metric, here's the radial direction. When rho goes to infinity, I eliminate the radial direction, so I'm going to get rid of it at some point. But then what I see is that the dt squared and the angular part, they both have an exponential dependence on rho. Beforehand, I was telling you that you should cut the exponential dependence on rho and just eliminate it. So we can do the same thing over here, and we can do a limit where we just take the metric and we call some hatted metric, which is the one that is induced on the boundary. And then there's a factor that looks like exponential to rho, and g hat is the thing that kind of survives. And therefore, the correct way to define g hat, which is the boundary metric, is you take the metric over here and you take the limit when the rho goes to infinity, and then you dress it up with an exponential of -2 rho times g perpendicular. Yes?
Is this similar to the conformal factor that we
eventually it will become. The point is that if you do this, and you just strip this conformal factor here, which goes this way, you get this stuff, okay? You get minus dt squared plus the omega 3 squared. And let me remind you what this is. This is a time and a sphere, and that's a cylinder. So this is the cylinder. And when we were talking about the operators, the correspondence, We're talking about what happens when you do quantum field theory on the cylinder.
Not the same conformal factor, very similar.
No, it is similar, but it's not. So basically, we're using the same type of notion of boundary field value by removing the exponential behavior in rho. So I just, told you, in my favorite coordinate system, this is what I do. And then, of course, the question is, okay, this general relativity, you cannot just pick one coordinate system and say that everything is done with that coordinate system. What if, my friend over here comes in and says, use a different coordinate system? What are you going to do then? You're so smart. What if we change coordinates to a different system? Okay. So this is where a little bit of relativity really is telling you that you cannot just take the space, take the limit. I can do this if the space was rigid, but if this is really going to be general relativity, coordinates don't matter, right? I should be able to do this in other coordinate systems. So let's say that I pick a new rho variable, rho tilde, which is rho minus some function of theta and t. I just picked it out of a hat. We can still go to a coordinate system where the metric looks as follows. So I just write rho as rho tilde plus epsilon, and I stick it everywhere where I had it. So I have in the exponential to rho, I will get 2 rho tilde plus 2 epsilon with minus dt omega squared. Here I will get d rho tilde squared, and then I will get some mixed terms between rho and epsilon, that rho tilde and epsilon from this change of variables. And the idea is that they will be subleading, meaning they don't go like exponential of the to rho or exponential to rho in t and omega. So they can be in the dot, dot, dot. And then I'm further allowed to do a change of variables so that there's no mixed term between rho tilde and the rest of the variables by modifying t and omega with sub-exponential pieces that will also show up in this dot, dot, dot. So I can do a metric coordinate system which has an expansion where the d rho squared looks this way, there's an exponential of rho, and there's some junk over here. And then there's subleading pieces. And then this type of coordinate system is called the Pfeffer-Graham expansion. So there's a gauge choice about radial directions that says that when I pick my radial directions carefully, I have to pick them in such a way that they are perpendicular to all the other coordinates that I have around. And that's a gauge choice for the other coordinates. I have my radial direction, and I have my transverse directions. And then there's this statement about Pfeffer-Graham is that you can always choose coordinates to make it like this. But I got this epsilon, okay? So the coordinate t and omega are transverse to rho, meaning that there's no mixed metric element between t and rho. That's what the Pfeffer-Graham gauge is. There's some additional conditions I'm going to bury under the rug, meaning that rho has to be geodesic and some other stuff, but that's a slightly different problem. These coordinate gauge choice, as I said, is called the Pfeffer-Graham expansion. And then we want to play the same game in this new coordinate system, okay? So I just invented a new coordinate system. Things behave this way with the exponential of 2 rho tilde. So how do I get the limit metric? I take g hat, and I now take the limit when rho tilde goes to infinity, and I strip the exponential factor. That was my rule before. So I use the same rule. And then what do I get? I get the exponential of 2 epsilon theta minus dt squared plus d omega 3 squared. And why does the rest of the stuff don't matter? Is because the rest of the stuff is going to be subleading in rho tilde. So it goes to 0 when I take rho to infinity. So no matter what I did with the rest of the metric over here, in all these dot, dot, dot pieces, all of that goes away. We also had an S5. If you do this with the S5, you have to multiply it by exponential minus 2 rho tilde. So the S5 disappears. So I can get rid of the S5. So the boundary is really going to be this cylinder over here, minus dt squared plus d omega 3 squared. Okay, but I got a 2 epsilon over here. Okay, so now you remember, wait a minute, I know that was what you were telling us yesterday. This is a Weil rescaling. So by doing this change of coordinates, I was able to obtain a new boundary metric, which is the same boundary metric rescaled by a non-trivial conformal factor. Okay, so we have managed to change a boundary metric by Weil rescaling. And then the point is that when you take the limit, you cannot be blasé. You have to be careful about how you do it, because if you make different choices, you get different answers. Obviously, in gravity, if I choose a coordinate system or another one, I'm still going to get good answers. But what we mean by the extrapolate dictionary gets, polluted by these facts of epsilon. So we really need to be careful when we identify what we call the boundary fields. Okay. Yes. So G hat perpendicular is the directions that are perpendicular to rho. And then this is the induced metric on the surface at infinity. This is the way we define that surface. And rho is a radial direction, which is defined to be perpendicular to the surface at infinity. This is kind of the definition of what rho does. Yes. So you get the boundary metric by reading the exponential behavior, removing it, removing rho, and picking this stuff out. And you do it in the Favre-Gram gauge. Okay. If you're doing AdS 5, then there's one time direction and threes. It's a three sphere, and then this is a three sphere and a time. If you're doing AdS in D dimensions, you get a time here, and you get the sphere of whatever dimension it is to get this thing to be dimension one less than the original AdS space. Okay, so I got a boundary scaling. So what happened to the boundary field? Well, I need to take the limit when rho tilde goes to infinity of the boundary field. And then when I take rho tilde instead of rho, I know how to write rho tilde instead of rho. So what happens is that there's the difference between rho and rho tilde is a factor of epsilon. So you eat up this factor of epsilon in the extrapolate dictionary, and you find that this F tilde transforms the same way as the original extrapolate dictionary that I have, the one with rho rather than rho tilde. And then I pick up a difference factor of the boundary scaling in the limits. So when I take this one over here and compare it to the one that I did with the original procedure, I get the same answer up to something that depends on this epsilon that I chose, which is the boundary scale. Okay, this is why, this is the really important point, is that if you think of this as an operator in conformal field theory, and you think about this as a boundary scaling, and you see this factor over here, it's something that tells you that this gadget is behaving the same way as operators do in conformal field theory. So in conformal field theory, if you have an operator, and you think of the operator as computing some expectation value, the expectation value will transform in this way. So this F tilde over here, transforming in this way, is transforming exactly the same way that expectation values do in conformal field theory when the expectation value is of an operator of dimension exactly equal to delta. Delta was the energy of the state. It was the thing that controlled the representation theory. And now it's also showing up in the way the same delta over here is controlling these expectation values boundary. So this works exactly like a primary field as a classical expectation value was in conformal field theory. And what I've just told you in this language is that I reproduce the word identity for conformal transformations in terms of these expectation values on the boundary. Okay? This is not the way it's usually presented in the literature. People usually don't go through these polynomials. Actually, I haven't seen that written down anywhere. I just do it because I like it. Okay? But this is the crucial fact that tells you that if things are going to work out, they have to work out in such a way that the operators that show up here, these things that we're computing, have something to do with operators that have the same conformal properties or the same transformational properties under boundary scalings. What? Right, so descendants come with derivatives, and then you have to be careful because the derivatives introduce additional stuff when you do changes of variables.
The F that you started with was
Sorry, the field, sorry. We were doing wave functions in the AdS. When I go to the boundary, I'm doing wave functions as they approach the boundary. This approach to the boundary is measuring something, okay? And I'm telling you that what that will measure is something that behaves like a field insertion of the same operator associated to something of dimension delta inserted at the position t and theta on the boundary. So different points of the boundary will have different functional forms when you do spherical harmonics of the interior. Just like when you do operator correlations, they depend on the angular coordinates depending on what you've inserted.
there is some kind of correspondence
Right. Yeah, but I'll get to that. Okay. So this is what's usually called the extrapolate dictionary. So extrapolate dictionary means that you take your coordinates, you go to infinity, and you have to be careful how you go to infinity. And once you do everything right, you can understand that certain values of these extrapolate fields behave exactly like expectation values in conformal correlators, right? In that they have the same wild transformation properties as correlators in my favorite conformal field theory. And the same happens with the metric. I was able to recover a metric by doing carefully the limit, the same type of limit, and then I get the boundary metric.
Yeah, I don't know if you want to go here, but if you now take, say, a 4-point function and divide by products of 2-point functions, they entirely cancel. So you get exactly the same function of the cross ratios.
Yeah, but this is not what we're doing. This is not how you do it in AdS.
No. In the conformal theory,
yes,
this factor cancels. It's a sort of trivial factor that cancels in homogeneous ratios.
right? Yes.
So yeah, so that's very useful.
So there's some things that are independent of these choices. That's what you're telling me.
I'm saying that the cross ratios actually depend on the original t theta coordinate system.
Yes. Okay. Very good. Okay, so let me tell you what this limit means. So I just told you that I can pick some random cutoff, not cutoff, but I pick some random coordinate and then I take the limit. The question is, why do I have to do that in the first place? Okay, why do I need to pick a radial coordinate and do that? And you have to think about the gravity action. You cannot define the gravity action directly in global AdS because AdS has infinite volume. And when you have, let's say, things like the cosmological constant that measures the volume, then the fact that you have an infinite volume means you have an infinite action, and who can work with an infinite action? So the point is that you're supposed to work with a finite action. So how do you do that? You first cut off the infinity that is problematic, meaning you, instead of going all the way to infinity, you pick some random surface over here and you cut off the surface over there and you say, okay, I'm going to work with gravity inside this region, then my classical action is finite and I can do stuff. And then I try to understand how to take the limit when I go to this stuff, to infinity. So defining the action, when you have this boundary that I introduced, always requires adding boundary conditions for your fields. You cannot have a well-defined variation problem on some region without defining boundary conditions. And then on top of that, if you've actually looked at textbooks, you can also have sources on the boundary and extra terms that involve the fields added on the boundary. So the variational problem that you study can have stuff in the interior and there can be stuff on the boundary, okay? So I'm going to add sources on this finite boundary. So let's look at what we did. Why do we need a space-time cutoff? The volume of AdS is infinite. And there are infinities that arise from this infinite volume that need to be regulated. Okay, I'm using the language of field theory for a reason. So is that anything that happens on one side needs to have some meaning on the other side. So if I did this regulation over here, this regulation is happening off at places where the blue shift is going to infinity. Rho to infinity means high blue shift. What does high blue shift mean? It means high energy, right? It means very, very UV degrees of freedom. So the idea is that these infinities that are showing up from the volume must correspond to some infinities in the CFT dual. What infinities could be there at, the deep UV in the sense of having a big blue shift? It has to be something that has to do with regularization. So you have to, when you do field theory, you cannot just do field theory and claim you know the answer. You have to regulate the UV. This is part of what we've been seeing with Anna's talk and regularization. So there has to be some UV structure that regulates the theory. In gravity, this is infinities that show up from the infinite volume need to correspond to the UV structure regularization somehow. This is what's usually called the UV-IR correspondence. The UV problems in field theory are an infrared problem in gravity in the sense that I had to put a geometric cutoff at some finite volume. So you can say that gravity has geometrized the regularization procedure in conformal field theory. Geometrized means that instead of talking about cutoffs as something that I have to do locally in the UV of the field theory, I've turned it into a problem of gravity where I say it's a geometric cutoff far off, close to infinity, but it's done, okay? So going to the UV, in this case, means you increase the blue shift. So you increase the size of the regulated gravitational box. So you increase the volume. So increasing the volume is going to the infrared. Okay. This is the UV-IR correspondence. It doesn't go the other way. That doesn't mean that UV problems in gravity become infrared problems in conformal field theory. That's not what happened. What happened is that the UV problems in conformal field theory can become geometrized to infrared problems in gravity. It doesn't go the other way. Right? It's not that every UV thing has an IR correspondence. Some UV things have an IR correspondence. Okay, so what's the cutoff action in this case? If you have the action of the boundary, there's the induced metric, which is this perpendicular metric. I fixed it at fixed rho star, so it needs to be the induced metric that's perpendicular to my choice of rho. Then there's my field, F. The square root of G perpendicular grows like some e to the d times rho, so it has some exponential growth. The F has its own exponential decay. You keep that information and you kind of put it in here, and then you add it so that when you take the limit is well defined. So what that means is that the S star, which is what we usually would call the source, needs to be dressed up with a factor that includes this d rho star, so that I can define it sort of as something that lives in the full bulk that includes both of these behaviors. And if you read what's the dimension of the source, you get this d plus rho, so it's d minus delta. This is what we would call the dimension of the source, okay? And as you can see, the dimension of the source is the opposite of the dimension of the operator, and there's this factor of d. This factor of d was showing up in the definition of this mass squared. This d is also the fact that you're in d dimensions, and the volume measure carries some measure factor, okay? So you call the source kind of normalized and take away the volume. So because this has a different exponential dependence, if delta was positive, then delta source is negative. This will be very badly divergent at infinity. So the idea is that these things grow too fast to be fluctuating, and then you have to freeze them to some value. When you freeze these things that blow up at infinity, this is when you claim that you have a source, that you've added a source to a field. And the claim is that when you have a source, you produce a non-trivial solution of the wave equation, which has a source on the boundary, and it'll blow up near the boundary because sources usually kind of make things blow up near them. Okay, so this is important. The classical source on the boundary basically gives rise to solutions of the same equation of motion in the bulk for a field, but they are non-normalizable. So I have to split always between normalizable and non-normalizable solutions. And the ones that behave normalizable are the things that I call oscillations in the Hilbert space. These are these fluctuations. And then the stuff that is non-normalizable is the stuff that I call a source on the boundary. Okay? Because they're so big, they cannot oscillate any longer, that they have an infinite norm. Okay, so now finally, after all this, we solved the wave equation, we picked up the normalizable modes, we picked up the non-normalizable modes, we can finally quantize. So how do you quantize? To each normalizable partial wave, solution in the bulk that decays sufficiently fast, you assign a raising and a lowering operator, right? For each solution of the wave equation with different frequencies for each normal mode, you have to assign a quantum field creation and lowering operator. When you think about classical solutions, one quantum is a one particle state. And then if you have a quantum field theory in the bulk, you can have one particle states, two particle states, three particle states. So it better be that the conformal field theory can have two particle states, three particle states, four particle states. Right? There needs to be something that counts the particle states so that the notion of particles in the bulk can be matched to something that is reasonable on the boundary. I put this thing out of order. But here's the other thing. I'll get back to this. Here's the other thing. If you look at the perturbative solutions meaning solutions of the wave equation. I told you that in the Extrapolate dictionary, I pick up the different Fourier modes. The different descendants have different frequencies, and they have different spherical harmonics on the boundary. So I can pick apart the classical solution to the equation of motion by doing a Fourier integral on the boundary with spherical harmonics. So I can read the classical field values from the amplitudes from this Extrapolate dictionary. And if you think about it, in gravity, when we talk about solutions of the wave equation, they're coherent states. So what you're doing here is you're trying to calculate the amplitude of these coherent states by looking how it goes to infinity. And this is what the process of measuring the classical field will do on the gravity side. And measuring the classical field is basically calculating the expectation values of the lowering operators, so to speak. And then the operators on the boundary need to be doing something. They need to know something about this. The boundary, as I said, is the cylinder, and the different modes, different energy by integers. This was what I said. So now to match states and states, the Hamiltonian on the CFT needs to be the Hamiltonian on the gravity side. This is the equivalence of Hamiltonians. Our simple operator, meaning our raising operator, that generates the lowest weight state, needs to be mapped to some operator in field theory because we're using radial quantization. So it needs to be associated to something that creates a state of energy delta on top of the vacuum. So it must be an operator of dimension delta inserted at 0. This is how you insert a state at finite radius by using the operator state correspondence, right? So the operator evaluated at 0 gives you the A dagger. If you evaluate the same operator at some other value, it needs to be some combination of A plus A dagger. And then that means that when you measure O, you're measuring the lowering part of the operator. That's what the classical field will do. So measuring O on the boundary at some different place will be some other linear combination of A and A daggers that lets you measure it on the boundary. Okay? This is really important. The state is the operator inserted at 0, meaning at minus infinity in time. Okay? So who was asking me about this? How do you unmatch the gravity solutions to operators? I do it in the infinite past. Okay? So if I have a state in gravity, a normalizable solution with equation that's just sloshing around, that corresponds to a particular operator inserted in the infinite past. The solution is classical and sloshing around, then it needs to be something like a coherent states. It's some weird class of operator, not something of fixed energy. But if you do a fixed quantization with a fixed number of quanta, then these gadgets will naturally be something that has operators in them. Okay, for convergence, meaning for the integrals to be well defined, for us to have a proper L2 norm, delta needs to be bigger than 0. The analytic continuation in T. So we have these things sloshing in T, and now we want to go Euclidean. If you want to go Euclidean, you analytically continue in T. Makes the wave equation solutions go from e to the I omega t to the I. You strip the factor of I, and then they blow up in the infinite past. This is the same as the CFT intuition, that when you do a Euclidean correlator, something has to blow up when you go near the insertion of the points. So you start from Lorentzian and you go Euclidean, you find that the solution needs to have singularities in what's called the infinite past of the cylinder. And in some other coordinate systems, it means that there has to be a singularity at the place where you inserted the operator in the field here. Okay? So to insert a state in gravity, we need to have a source at the boundary. It's usually the infinite past. It's a non-trivial boundary condition in the infinite Euclidean past. Okay? So if you do a classical state in gravity, which is a coherent state, you write it as alpha, as exponential of alpha A dagger. The classical field is proportional to this coherent state parameter. In our correspondence, if A dagger was O, that means that alpha needs to be generated by something that looks like exponential of alpha O. And then you should complain because O has dimensions and alpha is just a number. You need to kind of clean this up a little bit, but this works. It's okay when you do it on the cylinder. When you do it on the Euclidean theory, this needs a bit more work. Okay, including descendants, alpha. You don't just generate the origin, but you add all the descendants. So you can add a generic state. So how would that look like? You add a coherent state for each one of the partial wave operators that I have, I have a coefficient for them, I have all my partial waves. And then if you look at something that has coefficients times partial waves, and these are derivatives, then you see, oh, wait a minute, this is a Taylor series. So I'm just doing an integral of alpha of x times O of x. So the claim is that to insert a more general state, you would just do something like an integral over a region of the integral of alpha x O x. That will be something that generates your preferred state in gravity. So inside correlations in the CFT, what we're getting is that alpha, which is the thing that controls classical gravitational physics, is acting like a source because it's showing up as the integral or the coefficient that's multiplying O of x in the generation of the state. And this is usually something that we would put in the action to generate it in path integrals. So the modified boundary condition in gravity is basically proportional to the strength of this source. So the non-normalizable solution of the wave equation is the thing that controls the source that you're putting on the cylinder. The normalizable part is measuring the state in the bulk. So you can either modify the state or you can just measure it. Measuring is computing these classical expectation values at infinity. And the other thing is adding a classical source at infinity. There's a slight distinction between raising and lowering operators, and the classical limit, you treat them one as a source and the other one as a sink. And the sink measures, and the source is the thing that generates new fields emanating from the point. So the normalizable part is the thing that we will usually call the expectation value of the field, which is measured by the expectation value of the operator of the cylinder. And that's the thing that has to behave and has the correct word identity to rescale in the right way that shows up in correlators. So the punchline, there's no punchline, is going to come in a minute. The other thing I told you is that there has to be multi-particle states. So how do you build multi-particle states? This is where how the AdS CFT correspondence came about is really important. The field theory that we studied was large N field theory, and at large N, the 't Hooft limit, there's theorems that guarantee that the theory will look like a free theory of something. Okay, it's a free theory of strings. The strings will be very weakly interacting. They have some notion of number of strings. You can talk about that number. So that requires a notion of multi-particles in the CFT. And this is what's usually called large N factorization. You can have two particle states and they don't interact. That means that you can treat them independently. You can factorize the problems of one versus the other one. Large N factorization is a generalization of that says that some correlation functions just, they don't talk to each other or they factorize. And then this large N basically is providing a notion of quasi-free composite particles. So when you take the product of two operators, the composite operator, which is two particle, can be thought of as a two-particle state because there's nothing going on in between these two operators. Okay, so when you start trying to understand what that is, in the large N limit, the particle number is the number of traces that you have in your operator. Again, this is something that works for a while until it doesn't, meaning that classical fields with a fixed number of particles cannot go all the way to infinity because in gravity, you'll get nonlinear effects, from black holes, you'll do all kinds of other stuff. So you get a Fock space for a while until it doesn't look like a Fock space. And in field theory, you get a Fock space for a while until it doesn't look like a Fock space. So large N factorization works for a while until it doesn't. This idea of quasi-free particles sloshing around in AdS works for a while until it doesn't. And then in the weak coupling limit, this can take a very long time, and you can have a lot of particles doing nothing, not talking to each other, and doing whatever they do. So there is a way to think about that limit as the limit in which this large N factorization is providing the relevant physics, meaning that the interactions are always suppressed by 1 over N squared. So you can really measure the number of particles and all the other stuff for a while. Okay, so what's the master AdS CFT formula for a dictionary? So the idea is that you do the partition function of gravity with some boundary condition that you fixed at alpha. Doing the partition function means you calculate gravity, classical plus semi-classical plus fully quantum. If you're like I am, or like most people are, we usually stop with the gravity calculation at the first order where the calculation gets hard, which usually is right beyond classical. So you do calculations in gravity with some boundary condition alpha for each operator that you have in the field theory that's single particle state. The That's equivalent to doing the partition function of the conformal field theory, meaning adding stuff in the conformal field theory, where the source of the conformal field theory for the operator O is matched with alpha. And I told you how that came about, being careful about how to take the cutoff of gravity to infinity and why you needed a source and how that source relates to coherent states. Okay. So the claim is that many times when you see holography, they say, okay, this is the dictionary. We start from here. It is a black box. You do conformal field theories with a source here. You do boundary with some boundary condition alpha. And then this is a black box where we can calculate here and we can calculate here and we can compare. The claim that I want to make today is that this is not a black box. We derived this to the extent that it can be derived. And there's no way about it. It cannot really work in any other way. All the word identities, everything points in the direction that this is the only way in which it can work. Holography tells you that, these observables of extrapolation are good gravitational observables because the volume of any small region, when you take it to infinity at fixed angles, has infinite volume and infinity. And infinite volume and infinity means that the fluctuations on top of it are of order 1 on top of infinity, so the volume stays infinity. So that number over there is some well-defined average value of some gigantic region of space-time that doesn't fluctuate. So these boundary conditions are well-defined gravitational objects. And the claim is that because of that, you can do quantum on both sides and be safe and do calculations. And the claim today is that this is the way it works. And when you see many AdS CFT reviews, this is where they start. They say, this is the dictionary. Normalizable modes are particles and stuff like that. Non-normalizable modes are sources. And this is the magic formula that gets you to relate one to the other one. Okay. The claim today is that this is not magic. This is derived. And you really have to be careful about it. And the way the derivation worked today, which was really important, is we did it in Lorentzian space. We didn't do Euclidean. We went Lorentzian from the beginning. This was really, really important. Okay, what happens when you have continuous symmetries? So conformal field theories sometimes have additional symmetries. They're characterized by some current that is conserved. And remember, d mu is the thing that generates descendants. So if you see d mu, j mu equal to 0, that means some descendant is equal to 0. This is the equation of motion of conservation of the current. What that means is that the descendant is 0 as an operator in conformal field theory. So this is equivalent to having descendants, meaning derivatives of operators that you know, that are null, meaning that they're identified as 0 over there. And these are short representations of the conformal group. Some descendants are missing. We call those representations where some states that would otherwise be there absent, short. And the descendants of a null state are also null. This is something that usually happens. So a note of caution is upper and lower indices can transform differently when we rescale the metric, because they differ by rescaling by a factor of G inverse. So you have to be careful when you talk about the dimension of these objects, whether upper index or lower index. You have to kind of work a little bit more carefully. So you need to watch out. I'm not going to solve that problem here today. What I tell you is that this translates to something interesting in the bulk. So if states that will always be there are absent, that should also be true on the gravity side. The states that would otherwise be there are absent. And it's not just one state that is absent. It's an infinite collection of states because descendants of null are null. So what that means is that you have to have a theory where the typical particle that you have has some missing polarizations in the bulk. How do you do that? You require the particle to be massless in the bulk, plus a gauge symmetry to remove the unphysical states. So the idea is that if you have a conserved charge on the boundary, then that should correspond to something that is a short representation in the bulk. And to make something short in the bulk, you need to eliminate the unwanted states. To eliminate the unwanted states, you need to have a gauge symmetry to get rid of them. And you need to have the particle be massless. So basically, the current J mu gets mapped to something like an electric field in the bulk. And then the source for J mu, right? We said that there's a source. The source for J mu, because J mu is conserved, the source for a J mu always has a gauge symmetry in the sense that you can shift the source by some finite amount, and then you integrate by parts and use the conservation of J mu to eliminate some terms. So that gets mapped to some kind of notion of the bulk gauge field going to infinity in some gauge. And because this is an infinity, this becomes frozen. So you cannot just gauge it away automatically completely. Okay, really important. The source is kind of gauge variant in some sense. Okay, so if you have a conformal field theory that is canonical, it has a conserved stress tensor. That's a spin 2 current that is conserved. So you have to have a spin 2 particle in the bulk, which is massless, which has a gauge symmetry. So what is that? A spin 2 massless particle in the bulk with a gauge symmetry, gravity. So the point of AdS-CFT is that if you start with this idea and you just want to do it on rigid AdS, and you know that the conformal field theory has a stress tensor that is conserved, therefore there must be a fluctuating degree of freedom in the bulk that corresponds to that stress tensor multiplet, and that does via the operator state correspondence and identification with something. This is a gravity field in the bulk. So when you do AdS-CFT, you have Einstein gravity in the bulk. This is something that you, so to speak, get it for free, meaning you cannot do AdS-CFT without gravity. Okay, so this is the evidence for the law that all symmetries in quantum gravity are gauged. So, you know, the symmetries that came from the boundary that were global become local symmetries in the bulk. When you add supersymmetry, stuff happens. I'll skip this until tomorrow, but it's not too much. The idea is that we got to the magic bullet today, which was this one, that we have this parameter, and then the other thing that we got for free is that if the conformal field theory is regular, you have gravity in the bulk. Okay, so gravity in the bulk, the fact that in AdS you get a theory of gravity is unavoidable. You cannot skip that part. Okay, you cannot just say, forget gravity in AdS. That's not what the dictionary will tell you. You need to do gravity in AdS in the end. Okay, I'll stop here.
Okay, thanks, David. Time for questions. Oh, yeah, there is a question behind.
Yeah, we'll take turns. Go ahead and then.
Yeah, you said that some part of the Fock space you can sort of match, right? As
Yes.
like free particle states or quasi-particle states. Where do exactly the like bound states also fit in?
Okay, so when you do gravity, so this is gravity, it's a box. And if you have a 2-particle state over here, this is well described in free theory by 2 individual particles. Once you add interactions, it is well described by 2 particles with a weak interaction between them. So what you would see here is that the 2-particle state, the energy of the 2-particle state, will be the energy, twice the energy of a single particle state, plus a small correction. The small correction would be induced by the interactions, but this small correction is of order 1 over n squared. Okay, so the idea is that bound states do show up, but they usually show up suppressed in as a small shift in some multi-particle state with a very small shift. When n is not small, the small correction is not small, and therefore stuff can happen. What's the other way in which things can happen? For 2 particles, it's not a problem. When you do many particles, you get n particles in the bulk, and the small correction will come from all the interactions between all the particles, and it scales different with the number of particles, so it can become a big effect that piles up and tells you that this small correction added over a lot of particles becomes a very non-trivial binding energy for something bulky. Okay, so for small numbers of quanta, the perturbative analysis is okay. Once the occupation numbers get big, because you're in a finite box, you're at finite density, and finite density, these binding energies and all this stuff start mattering, and they can produce very non-trivial physics, like stars and black holes. Yes.
So we were talking about matching the primaries and the secondaries, right?
Yes.
In both. So if we have already matched the primaries and we have matched the raising and lowering operators, do we actually need to map the secondaries? Aren't they already mapped to each other?
They come automatically in the sense that the secondaries or the descendants are generated by group theory on both sides. So if you know how to do it on one side and you know how to do group theory on the other side, you can establish the Krebs-Gordon coefficients that do the dictionary carefully enough to make sure that once you have the primaries, the rest follows by group theory. It's not trivial, but it's not infinitely hard either.
More questions? Rich, go ahead. There is a question.
Just wait. There's someone else on the
Somebody
microphone
in the back.
is
Somebody in the
matching.
back. Yeah.
Yeah, so the epsilon theta t function that you used,
Yes.
where you define a new rho tilde for going to infinity,
Yes.
was that just different ways of taking the infinite rho goes to infinity limit?
Yes.
And that epsilon was the one which induced some conformal transformation in the boundary theory.
So I cheated. I said what I didn't tell you is exactly why I chose the coordinates that way. Why did I choose an epsilon that depends only on theta and time and not rho? The idea is that usually you want to do a change of coordinates which asymptotically looks like that plus extra junk. So there will be subleading corrections that don't matter at infinity. So you can just start with a change of coordinates which starts like that. You put it in the change of variables, and then you fix everything else by requiring that this Pfefferheim-Graham condition is satisfied. So the claim is, if I want to match my coordinates at infinity, there's an ambiguity on how I do that. And I was trying to just capture that ambiguity without doing the full nonlinear change of variables in full detail.
That ambiguity is captured by the theta t
By the epsilon term, yes.
Okay.
Yeah.
Will cover it like I'm saying like for HKLL constructions, eh?
Yes.
Yeah, so we just need some scalar boundary scalar field to construct. So for that, the gravity is not needed. So, or
well, it is implicit in there. So in the boundary, you usually have specified already what metric you have, and that metric implicitly has defined this limiting procedure for you. So if I specify what the metric is on the boundary, I've already told you how I took that limit. So I've already told you implicitly what I did. If I rescale the metric on the boundary by some epsilon, then usually it becomes curved and not flat and not pretty, and then nobody wants to do calculations on that. If I pick it flat, I've already told you how I did the limit in a particular way. Okay, so if I tell you what the metric on the boundary is, I've already skipped the part of how did I derive it in detail and told you I did it this way, and then you just have to do the calculations what I gave you.
for say some subregion, for say some subregion construction in HKLL. So there are some various problems like this. Probably you will cover in the next session.
I'll try to cover some of
Yeah.
it.
So I was
I'm
saying,
not sure that I'll get everywhere, but
yeah, I was saying for those problems, is gravity needed, like to solve those problems, these ambiguities and this? Or it is some quantum field
there's
theory.
different classes of ambiguities. So there, what's needed is something else. Some ambiguities are related to the fact that more than one Fourier integral might give you the same number in a place, okay? That if instead of doing, let's say, things from 0 to 2 pi, I went from 0 all the way to 4 pi, there would be a lot of different constructions that would reproduce the same number by different Fourier transforms, because I took a lot of extra time. And then you would say, oh, but if I do the construction this way or that way, I get different things. Yes, but in the end, you're getting the same thing. It's just that it's over-encoded in some sense. So there can be more than one way of representing the same thing, the same solution, because you've covered a patch that does things with redundancy. And then you have to specify how to get rid of that redundancy. And that's part of what I think you're trying to refer to. But it really has to do with the fact that you chose a patch that's big. That's good. Okay.
Maybe Rich had a question.
Yeah, back on your bound state question here.
Yes.
Normally,
Do it on the microphone, sir.
Normally, if you had a short range weak force, there would be no bound state. It would be scattering, but no bound state. So are you saying because of gravity, you're going to automatic. And first of all,
Okay, you're in a finite box.
no, you're not. The distance to the wall is infinite. You're
No,
an
it's
infinite volume.
no, it's a finite box because there's this barrier over here, which is a tunneling barrier. So it acts effectively as having a finite cutoff for your field. So AdS is a box.
No, you're right.
It has infinite volume,
Yeah.
but it reflects stuff. So if you have a low energy, you get reflected.
No,
rather
you're,
quickly.
you're right. It is an infrared cutoff. You're right.
So it's an
Right.
infrared cutoff. You're in
Yeah.
a box. When you have two free particles in a box, no matter how weak the attractive interaction is, you get a small correction to the energy. And then the question of having a bound state in flat space is when I take the box to infinity, does the binding energy go to zero so quickly that the bound state disappears, right? That's a different question of saying that when you have the two things, if they're attractive, there's a small
No, but
downshift in the
I get
energy.
you right. But if the box is finite, you can never get to an asymptotic separation. That's the real problem. So it's really
Right.
somewhat of a question of definition, right?
Right. So this is the
I
statement.
mean, you can call it a bound state or not, but
Right.
it is what it is. Okay.
No, it's a bound state only in the sense that the energy is smaller than
Well,
the two
because
free
you can
particles.
never separate them, right?
Sure,
It's
but
a
that's
different
okay.
energy. Right?
The question was, how do I deal with bound states? This is how you deal with bound states.
But I'm just saying, it's really to call it a bound state is sort of it's the box is finite. You cannot define the question of two particles separating, right?
Not enough. That's right.
Right. I mean, there's no S matrix.
Yeah, but the point is that there is a binding energy.
Okay, so then now I have a question which is more fundamental. Conformal field theories on the boundary do not have to have an energy momentum tensor.
That's
sorry,
right.
I'm sorry.
Statistical mechanical systems.
No, I'm
don't-
sorry. There are conformal field theories that do not have an energy momentum tensor.
Yes, I don't know what to do with those.
What? No. So therefore, my question is, I'll tell you my opinion. I think there is an AdS CFT correspondence, which isn't gravity. I just see no
That's
reason.
fine.
So I mean, there's no necessity for an energy momentum tensor. Of course, it's very interesting to include gravity, but in fact, since I'm actually trying to do numerical calculations, it's easy to start with simpler system, right?
I was very careful. It says CFT plus conserved stress tensor. So if
No,
you
but
assume-
but your comment after was it's very important to have a stress tensor to do all this formalism. Actually, it's not. You don't. All the formalism you described all the way through had nothing to do with gravity in terms of how you went from the bulk to the boundary.
No, but part of the thing that I told you in my definition
Yes.
of conformal theory is that I can couple it to gravity on the boundary. And to do that, the definition of the stress tensor is the derivative of that thing coupled to gravity.
No,
with respect to
but
gravity.
all your formulas, as far as I could see, that tried to relate a bulk field to a boundary field was
Right.
independent of gravity.
That part is independent of gravity.
And so that's AdS CFT, period.
No, that's the AdS CFT extrapolate dictionary. What I'm being very careful about is that when I define CFT, I said you can put it on any Riemann surface of geometry that you want. It can be the case that there's things without a stress tensor, but it might not be the case that I can put it on a random geometry any longer, that geometry might be rigidified in some way. It might still be the case that you have global conformal transformations and some stuff like that.
No, I'm saying there's a completely kinematic situation here.
Yes.
If it's AdS space, then the isometries of AdS space is the conformal group.
That's right.
And therefore, no matter what I throw into the bulk, I will get some kind of strange conformal. In fact, in the bootstrap, we have all this accepted region, no man's land. It's filled with all probably zillions
Yes.
and zillions of conformal field theories, right? So
Okay.
if you want to go into no man's land and some people in condensed matter like to do that, okay?
Okay, so here's
so
the
then
thing. If
there's nothing about gravity in the bare bones AdS CFT,
that's right.
right?
What I'm trying to get at is something very important.
Yes.
I defined the CFT as something I could put on a random geometry. I said that CFT is something that I can couple to gravity. The only way that I know how to couple a conformal field theory to gravity is by having a stress tensor.
I agree. So, but I'm just saying it's irrelevant to the statement of AdS CFT.
It's irrelevant to a statement of how to get the extrapolate dictionary.
It's irrelevant to the existence of AdS CFT as a phenomena. That there will always be a conformal boundary theory.
Right,
no matter
there will
what
always be a
crap you
conformal
throw-
boundary for some field theory in rigid AdS.
Right.
That doesn't mean that it's a good theory in the sense of being local and satisfying all the axioms that we would usually associate with conformal field theory, which many times include having conserved stress tensor. Right, this is the right? Usually when you say you can couple it to gravity, it means that you can define the stress tensor by.
I'm not just being, you know, difficult for the sake of difficulty. If you want to move into non-perturbative phenomena in ADS
Yes.
space, you're really, you're making too heavy a lift to immediately go to quantum gravity. There's a whole set of things you can do to understand this.
Again,
at a lower level, right?
The punchline is most
Rich.
conformal field theories that we know and love, like n equal 4 Young Mills, have a conserved stress tensor.
I mean, for example, suppose the boundary is only two-dimensional.
Yes?
Gravity isn't really much of a deal.
No, but there is a conserved stress tensor, and that's actually what gives us the whole stuff of conformal field theory. And the conserved stress tensor, when you put it in correlators, gives you all the Warren entities that let you solve the theory.
Right, but then you have to do three-dimensional gravity, which is very peculiar.
Yeah, so you do it.
Could I
You still have
make
gravity in the
could I make a
boundary.
comment, please? Shall we go for lunch?
Yes, let's go for lunch.
So there will be a discussion session after the last lecture, and let's continue with the discussions. Yeah. Let me check whether Zoom participants, whether they have any questions. So participants on Zoom, any questions? Looks like I don't see any. So let's thank David for a nice lecture.